In July 2025, astronomers detected an interstellar object moving through our solar system with a speed, trajectory, and chemistry that immediately broke expectations. It was named 3I Atlas. Its path aligned closely with the solar plane. Its emissions were dominated by carbon dioxide, not water ice, and for a brief moment, even respected astrophysicists asked a provocative question. Could this be technology rather than nature? Delayed images, public speculation, and sharp debate followed. Then the data arrived. What emerged was not proof of aliens, but something far more instructive about how science tests extraordinary claims. Stay with us, like the video, subscribe to the channel, and let's follow the evidence to where it actually leads. 7 billion years ago places this object in a period of the galaxy that predates our Sun by a wide margin. At that time, the Milky Way was already old, but its familiar structures had not yet settled into the form we recognize today. Many stars that exist now had not formed. Others that once burned brightly were already reaching the end of their lives. In one of the older regions of the galaxy, far from where the Sun would later emerge, a planetary system was evolving around a different star. Within that system, solid bodies formed from the same process that builds planets, moons, asteroids, and comets everywhere. Dust grains collided, stuck together, and slowly assembled into larger structures. Over time, gravity shaped these materials into stable orbits. But stability in a planetary system is never guaranteed forever. Small changes accumulate. Orbits shift. Massive planets migrate. Nearby stars pass close enough to disturb the balance. At some point, a gravitational disruption occurred. The exact cause cannot be known with certainty, but the outcome is clear. A large solid object was accelerated beyond the grip of its parent star. Once its velocity crossed the escape threshold, it was no longer bound. It left its home system and entered interstellar space, beginning a journey that would last for billions of years. Interstellar space is often described as empty, but that description hides important detail. It is not a complete vacuum. It contains thin clouds of gas, sparse dust particles, cosmic rays, and weak magnetic fields. The density is so low that collisions are rare, yet over immense spans of time. Even minimal exposure can alter a surface. Radiation slowly changes chemical bonds. Micrometeorite impacts accumulate. Volatile materials can be stripped away. What remains tends to be material that is physically resilient and chemically stable. As the object drifted through this environment, it passed regions shaped by stellar birth and stellar death. It moved through expanding shells left behind by supernova explosions. It crossed quiet regions where nothing much happened for millions of years at a time. There was no preferred direction, no destination, and no external control. Its motion was governed entirely by gravity and inertia. That long, uneventful journey continued until it intersected the outskirts of our solar system. In the summer of 2025, the object crossed a boundary where human instruments could finally detect it. Its arrival did not stand out immediately. Modern surveys scan the sky continuously, tracking thousands of moving points of light. Most of them are familiar types of objects whose behavior fits well-understood patterns. The initial detection came from a telescope located in Chile's Rio Ado Valley, part of a system designed to identify asteroids and comets that might approach Earth. The object appeared as a faint moving signal against the background of stars. At first glance, there was nothing about it that demanded special attention. It received a standard provisional designation and was placed into a queue for routine follow-up. That routine process is designed to filter out the ordinary from the unusual, as additional observations refine an object's position over time. Its trajectory and speed become clearer. In this case, those refinements produced an unexpected result. The object was moving far faster than a typical solar system body at that distance from the Sun. Measurements showed a velocity of roughly 60 kilometers per second relative to the Sun. Expressed differently, that is more than 200,000 kilometers per hour. This value immediately stood out. Speed in space is not arbitrary. It reflects the gravitational environment an object belongs to. Earth, for example, moves around the Sun at about 30 kilometers per second. That speed represents a balance between forward motion and the Sun's gravitational pull. Mercury, which orbits much closer to the Sun and experiences stronger gravity, moves faster, reaching about 47 kilometers per second. These speeds are well understood and predictable. At the distance where this new object was first observed, the escape velocity from the Sun is approximately 18 kilometers per second. Any object moving faster than that is no longer gravitationally bound. This object was traveling at more than 3 times that threshold. That single fact changed its classification. Instead of following a closed, elliptical orbit, the object's path was hyperbolic. A hyperbolic trajectory means the Sun can bend the path slightly but cannot capture the object. No matter how close it approaches, it will eventually leave the solar system and continue onward into interstellar space. Such trajectories are extremely rare in observations. Only a very small number of confirmed interstellar objects have ever been detected passing through our system. Even among those, this object's incoming speed was unusually high. That indicated it was not merely drifting slowly between stars, but arrived with substantial kinetic energy accumulated over its long journey. The Discovery team quickly recognized that this was not a routine find. They escalated the report and issued an alert through the International Astronomical Union's global notification system. This alert reached observatories, research groups, and space agencies around the world. Within days, coordinated observations were underway. Ground-based telescopes on multiple continents adjusted their schedules to track the object. Space-based instruments were also brought into the effort. The Hubble Space Telescope was tasked with high-resolution imaging, while the James Webb Space Telescope was directed to collect infrared data that could reveal composition and surface properties. As data accumulated, early estimates of the object's size began to circulate. These estimates were based on brightness, distance, and assumptions about reflectivity. Some models suggested a diameter between 10 and 20 kilometers to provide a familiar reference. That length is comparable to the distance from the northern tip of Manhattan to its southern end. Other estimates, based on different assumptions, suggested a much larger object, potentially approaching 46 kilometers across. While such early estimates carry significant uncertainty, even the lower end of the range placed the object among the largest interstellar bodies ever observed. The combination of size, speed, and trajectory made one conclusion unavoidable. This object could not have formed in the solar system. There is no known mechanism capable of accelerating such a large body to that speed while keeping it intact within our planetary neighborhood. Its origin had to lie elsewhere. Understanding why this mattered requires a broader view of how space is organized. Our solar system contains a vast amount of material, in addition to the 8 planets. There are hundreds of known moons, more than 1 million catalogued asteroids, and an enormous population of smaller fragments. All of these objects remain bound to the Sun, sharing a common gravitational environment. Other stars host similar systems, each shaped by their own formation histories. But the space between these systems is profoundly sparse. The distances are so large, and the density of solid material so low, that the passage of large objects from one system to another is exceedingly rare. When such an object does arrive, it represents a direct physical sample from another part of the galaxy. Between star systems, there is very little to speak of in terms of solid matter. That scarcity is precisely why the detection of this object drew such focused attention. It was not simply another rock passing by. It was evidence that material can survive, travel, and cross vast interstellar distances, carrying physical records from environments far beyond the Sun's influence. This also helps explain why such objects went unnoticed for so long. Gravitational systems tend to keep their material close. Once planets, moons, asteroids, and comets form around a star, gravity locks most of them into long-lasting orbits. These systems behave like closed neighborhoods, with objects circulating locally rather than freely escaping, for a long time. This led scientists to assume that while interstellar debris had to exist in theory, it would be extremely rare in practice. The theory itself was not controversial. Astronomers understood that violent processes such as planet formation, close stellar encounters, or massive collisions could occasionally eject material at high speed. Any object accelerated beyond its star's escape velocity would be lost to interstellar space. What remained uncertain was not whether such objects existed, but whether they could ever be detected. For decades, there was no direct evidence. Telescopes were not sensitive enough. Survey programs did not scan the sky frequently or deeply enough to catch small, fast-moving objects entering and leaving the solar system. If interstellar visitors passed through before, they did so unnoticed. That changed in the year 2017 with the discovery of the first confirmed interstellar object, later named Oumuamua. Even then, the detection was barely in time. By the moment astronomers realized what they were seeing, the object had already passed its closest approach to the Sun and was moving rapidly outward. The observation window lasted only a few weeks, leaving scientists with limited data and many unanswered questions. Despite the scarcity of measurements, Oumuamua behaved in ways that were difficult to reconcile with known categories of celestial objects. Its shape appeared highly elongated, far more stretched than typical asteroids or comets. Some estimates suggested it was several times longer than it was wide, giving it an appearance often described as cigar-like. This alone was unusual, but not decisive. More puzzling was what Oumuamua did not show. As it passed near the Sun, it did not develop a visible coma, the cloud of gas and dust that normally surrounds an active comet, nor did it produce a clear tail. These features are usually easy to detect, even with modest instruments. Once solar heating causes ice to sublimate, the most unexpected observation came later. As Oumuamua moved away from the Sun, it exhibited a small but measurable acceleration. This change in speed could not be fully explained by gravity alone. Solar radiation pressure was considered, but it also failed to account for the full effect. Something was pushing the object outward, This unexplained acceleration triggered intense debate. The most conservative explanation was outgassing. In this scenario, frozen material beneath the surface would slowly vaporize, creating a gentle thrust similar to a weak rocket. This mechanism is common in comets. However, the lack of a detectable coma made this explanation difficult to confirm. Other hypotheses pushed further. In 2018, Harvard astrophysicist Avi Loeb publicly suggested that Oumuamua could be an artificial object, possibly a thin light sail pushed by radiation from the sun. This idea attracted wide attention, not because it was widely accepted, but because it challenged scientists to confront the limits of their assumptions. While most researchers favored natural explanations, the discussion highlighted how little data was available. 2 years later, a second interstellar object was detected. It was named Borisov and designated 2I Borisov. Unlike Oumuamua, this object behaved much more like a familiar comet. Spectroscopic analysis, a technique that identifies chemical elements by the light they emit or absorb, revealed that Borisov contained unusually high levels of carbon monoxide compared to comets native to the solar system. This difference mattered, but it was not destabilizing. Carbon monoxide-rich comets are consistent with formation in colder environments. Aside from this compositional detail, Borisov displayed all the expected features. It developed a clear coma and a visible tail. Its motion followed gravitational predictions closely. Any acceleration it showed could be explained by standard outgassing processes as frozen material warmed and sublimated. In many ways, Borisov was reassuring. It demonstrated that not all interstellar objects would defy expectations. Some could be understood using existing models, even if their compositions reflected conditions very different from those near the Sun. That context is essential when turning to the third interstellar object ever detected. This is the object now known as 3I Atlas, named both for its classification and for the observatory that first identified it. Compared to its predecessors, it stands out as the most unusual so far. When data from the James Webb Space Telescope became available, scientists were surprised by what it revealed about the object's composition. Analysis showed that nearly 80% of the material being released was carbon dioxide. Only trace amounts of water vapor were detected. This ratio is essentially the reverse of what is observed in comets from the solar system. In local comets, water ice dominates. As they approach the Sun, water sublimates first, driving activity and forming the coma and tail. Carbon dioxide and other volatiles typically play a secondary role. For 3I Atlas, carbon dioxide was clearly the primary driver. This inversion challenged existing assumptions. Scientists proposed several possible explanations. One is that the object formed in an exceptionally cold region of its home system, far from its star, where carbon dioxide could freeze abundantly while water remained less dominant. Another possibility focuses on the object's long interstellar journey. Over billions of years, exposure to cosmic radiation could have altered its surface chemistry. Water molecules may have been broken apart, leaving behind a surface layer enriched in carbon dioxide. In this view, the composition reflects not just where the object formed, but how it aged while traveling through interstellar space. Additional anomalies appeared in the data. Observations from the Very Large Telescope in Chile detected vaporized nickel on its own. This was not unusual. Nickel has been observed in comets before. What made the finding notable was the absence of a corresponding amount of iron. In every comet studied within the solar system, nickel and iron appear together. They sublimate at similar temperatures. When one is detected, the other almost always is as well. For 3I Atlas, the iron signal was unexpectedly weak. This imbalance has no clear explanation yet and suggests differences in internal structure or formation history. While compositional studies continued, other teams focused on reconstructing the object's past. Astronomers traced its trajectory backward over roughly 4 million years. This was not a simple task. The calculation required modeling the gravitational influence of stars it may have passed near, as well as accounting for stars that no longer exist. The process involved simulating the object's motion through a changing galaxy. The Milky Way itself evolves. Stars move, form, and disappear to reconstruct the path accurately. Models had to include both present-day stellar positions and historical ones inferred from galactic dynamics. When this work was completed, a consistent picture emerged. The trajectory pointed back toward the region of the galactic core. More specifically, it suggested an origin in the thick disk of the Milky Way. The thick disk is a population of stars that orbit above and below the galaxy's main plane. These stars are among the oldest in the galaxy, formed when the universe was still relatively young and the Milky Way was still taking shape. This placed 3I Atlas not just beyond the solar system, but within one of the most ancient stellar populations known. In practical terms, it meant the object may have formed under conditions that no longer exist anywhere near our local region of space. If these interpretations were correct, then this object represented something very different from what astronomers had initially expected. It would not simply be another interstellar fragment passing through by chance. It would be a relic from an extremely distant past, formed long before the Sun existed, and preserved through billions of years of travel. Objects of that age are almost never available for direct study. This might be the first and only opportunity to observe such material at close range. One analysis led by Oxford astronomer Matthew Hopkins suggested that the object could be more than 7 billion years old. That estimate placed its formation earlier than the Sun, and possibly earlier than many of the stars in our local galactic neighborhood. If correct, 3I Atlas would be a physical sample from a time when the Milky Way itself was still assembling. At first, scientific attention focused on what this could reveal about early planetary systems. But that focus did not last long. Within a short period, a very different line of interpretation began to draw public and academic interest. It did not take long for someone to look at the growing list of unusual properties and ask a different kind of question. Less than 2 weeks after the object's discovery, Harvard astrophysicist Avi Loeb published a blog post with a deliberately provocative title, asking whether the interstellar object 3I Atlas could represent alien technology. This proposal did not come from an unknown or marginal figure. Avi Loeb is a former chair of Harvard's Astronomy department, the author of hundreds of peer-reviewed scientific papers, and a well-established researcher in astrophysics and cosmology. His work spans black holes, the early universe, and the formation of galaxies. At the same time, he is known for challenging conventional thinking and for presenting ideas in a way that attracts public attention. Loeb's argument did not begin with speculation about extraterrestrial intent. It began with orbital data. Specifically, it focused on the reconstructed trajectory of 3I Atlas as it moved through the Milky Way over millions of years. By modeling its path backward in time, astronomers identified roughly 93 individual star systems that the object would have passed during its journey. This alone was not unusual, over millions of years. even a straight path through the galaxy will intersect many stellar neighborhoods. What stood out was how distant those encounters were. To understand this point, it helps to clarify how astronomers describe distance. One astronomical unit is defined as the average distance between Earth and the Sun. A light year, by comparison, is roughly 63,000 astronomical units. It represents the distance light travels in 1 year. Throughout its long journey past those 93 stars, the closest 3I atlas came to any of them was about 1 light year. That is still an enormous separation. At that distance, gravitational interactions are extremely weak. Nothing about those encounters suggested targeting or capture. Yet after all of that travel, the object eventually passed through our own solar system at a distance of about 1.4 astronomical units from the Sun. That brought it well inside the region where planets orbit and where human instruments could observe it in detail. To Loeb, this contrast appeared striking. After millions of years of passing no closer than a light year to other stars, the object arrived unusually close to ours. On its own, this observation proves nothing, but it formed the first part of a larger pattern that Loeb believed was worth questioning. Another element concerned the object's trajectory alignment. Diagrams of the solar system are often drawn as flat, with planets orbiting in neat circles on a single plane. This simplification reflects a real physical effect. The Sun's gravity and the shared angular momentum of the planets keep most orbits close to a common plane. However, the solar system itself is not aligned with the Milky Way. Relative to the galaxy's main disk, the plane of the solar system is tilted by about 60 degrees. Objects arriving from random directions in interstellar space should approach from a wide range of angles. 3I Atlas did not. Its path was closely aligned with the plane in which the planets orbit. It passed through the solar system almost edge-on, following the same general flat geometry that defines planetary motion. Loeb calculated the probability of such an alignment occurring by chance at roughly 2%. Probability estimates like this depend heavily on assumptions, and many astronomers questioned the calculation. Still, the alignment itself was real, and it added to the sense that this object was not behaving like a typical random interstellar visitor. Timing added another layer. The trajectory brought 3I Atlas into the inner solar system in a way that placed it near the orbits of the rocky planets. It passed Mars, then Venus, and later crossed the region near Earth's orbit. At its closest approach, it passed Earth at a distance of about 1.8 astronomical units, nearly twice the distance between Earth and the Sun. This was close enough for observation, but far enough to pose no threat and to limit the level of detail that could be captured. To some observers, including Loeb, this appeared finely balanced. The object was visible, but not easily studied at high resolution. It was close, but not close enough to interact strongly or be captured. The timing of perihelion added to the discussion. Perihelion is the point in a comet's orbit when it is closest to the Sun. This is usually when cometary activity peaks. Solar heating drives sublimation, producing jets, gas clouds, and dust tails that reveal much about an object's composition and structure. For 3I Atlas, perihelion occurred when Earth was positioned on the opposite side of the Sun. From our perspective, the Sun's glare effectively blocked direct observation during the moment of maximum activity. Ground-based telescopes and many space-based instruments could not observe the object clearly at that time. This alignment was not unique in astronomy. Such configurations happen naturally, but combined with the other factors, Loeb argued that it reduced access to the most informative phase of the object's passage. Taken together, these features formed the basis of Loeb's case. Individually, none of them proved artificial origin, but he argued that the combination was difficult to dismiss as purely random. By this point, Loeb had positioned himself as the most visible proponent of the idea that 3I Atlas could be artificial. To formalize his thinking, he introduced what he called the Loeb scale, a ranking system from 0 to 10 intended to express how likely an interstellar object might be to have an artificial origin. On this scale, a 0 would indicate a completely ordinary natural object, while a 10 would suggest overwhelming evidence of technology. Loeb placed 3I Atlas at a 6. In scientific terms, this was a bold claim. Values above 8 would generally be considered extraordinary and unlikely without strong evidence. At a rating of 6, Loeb stated that he believed it was more likely than not that the object was not a natural comet, but an artificial construct. This position drew widespread attention and criticism, as well as careful rebuttals from other scientists. Over time, as more data became available and alternative explanations were considered, Loeb revised his assessment. He later adjusted the rating downward to a 4, acknowledging that the evidence for an artificial origin was weaker than he had initially suggested. That revision, however, came after the idea had already escaped the boundaries of academic debate. The original ranking did not remain confined to scientific circles. Once it became public, it spread rapidly across the internet. Popular culture figures began referencing it in casual ways that would have been unthinkable for a technical discussion only days earlier. One widely shared example came from Kim Kardashian, who posted a short message asking what was going on with 3I Atlas. The wording itself mattered less than what it represented. By that point, the object had moved far beyond astronomy forums and research papers and into general public awareness. This level of attention marked a turning point. What had begun as a technical discussion about orbital mechanics and composition was now part of mainstream conversation. Well-known public figures began weighing in. Elon Musk and Avi Loeb both appeared separately on widely watched podcast programs, including an episode of The Joe Rogan Experience. Each appearance reached millions of viewers and amplified the discussion even further. For many people, these conversations were their first exposure to the idea of interstellar objects at all. The distinction between speculation and established evidence was often lost as short clips circulated online. Still, the broader attention ensured that 3I Atlas became one of the most widely discussed astronomical discoveries in recent years. As interest peaked, timing added an unexpected complication. Just as 3I Atlas was approaching its closest pass to Mars, the United States government entered a shutdown. This was not a rare or coordinated event, but a result of ongoing political deadlock in Washington. Federal agencies, including NASA, were required by law to suspend most non-essential operations. Among the activities affected was public communication. While mission-critical operations continued, NASA was prohibited from releasing new images, updates, or press briefings related to ongoing observations. This legal restriction came at the worst possible moment. Anticipation had been building around the Mars flyby. 3I Atlas was expected to pass significantly closer to Mars than to Earth. Unlike Earth, Mars currently hosts a network of orbiters and surface missions equipped with scientific cameras. Some of these instruments are among the most advanced ever deployed beyond Earth. The Mars Reconnaissance Orbiter carries a camera system known as HiRISE. short for High Resolution Imaging Science Experiment. It is the most powerful imaging system operating around Mars, designed to capture detailed views of the planet's surface from orbit. On the ground, the Perseverance rover also carries imaging equipment capable of observing the Martian sky. Although none of these instruments were designed to image fast-moving objects tens of millions of kilometers away, scientists hoped they might still provide clearer views than Earth-based telescopes could manage. The idea of seeing 3I Atlas from another planet added to the sense of anticipation. The observations themselves were carried out largely as planned. Instruments were tasked, data was collected, and images were transmitted back to Earth. What could not happen was public release. For more than a month, the data remained inaccessible to the public and even to many researchers outside the agency. This period became the longest government shutdown in United States history. From a public perspective, the optics were poor. An object that a prominent Harvard astrophysicist had publicly suggested might be artificial was being observed by NASA, and yet no images or official updates were being released. It is not difficult to understand why speculation flourished in this environment. Social media platforms filled with claims that NASA was hiding something or that the shutdown had been deliberately timed. These ideas spread quickly, despite the fact that the shutdown followed a familiar political pattern rather than any extraordinary coordination. The speculation was not limited to anonymous accounts. Representative Ana Paulina Luna, a Republican member of Congress from Florida, sent a formal letter to NASA demanding the release of the images. The request did not result in any immediate action, not because of refusal, but because the agency's hands were legally tied until Congress resolved the funding dispute. As the wait continued, misinformation escalated. Artificial intelligence-generated videos began circulating online. These so-called deepfakes featured well-known scientists, including Neil deGrasse Tyson and Brian Cox, appearing to make alarming statements about 3I Atlas. In the fabricated clips, they claimed the object was an alien vessel and suggested that governments were concealing the truth. Some versions went further, warning of catastrophic outcomes. None of these videos were authentic. They were entirely fabricated using publicly available footage and synthetic audio. Despite this, many viewers were unable to distinguish them from real interviews. The combination of silence from official sources and the apparent authority of familiar faces made the false claims convincing to a significant audience. Throughout all of this, the object itself continued on its path. Comets and interstellar visitors are indifferent to human attention or political processes, while debate intensified on Earth. 3I Atlas passed perihelion, rounding the Sun and beginning its journey back toward interstellar space. By the time the government shutdown ended on November the 12th, the most critical phase of observation had already passed. The object had survived its close approach to the Sun, losing perhaps around 10% of its mass in the process, but remaining structurally intact. Its activity declined as it moved outward, becoming harder to observe with each passing day. NASA moved quickly once legal restrictions were lifted. About a week after the shutdown ended, the agency released the long-awaited images and held a press conference to discuss the findings. The event would later be remembered for a phrase that circulated widely online: "It is a comet." For many members of the public, the images were deeply disappointing. Expectations had grown unrealistic during the long delay. Descriptions of HiRISE as the most powerful camera in the Mars system had led some to imagine crisp, high-resolution views revealing detailed structure. The reality was far less dramatic. Images from the Perseverance rover showed an elongated, blurred streak crossing the Martian sky. The motion of the object relative to the camera made it impossible to resolve fine detail. The high-rise images were only marginally better. That camera was optimized to photograph the Martian surface, not distant, fast-moving targets. NASA emphasized these limitations during the briefing, but many viewers remained unsatisfied. To them, the images seemed anticlimactic, especially after weeks of anticipation and speculation. NASA was not alone in observing the Mars flyby. The European Space Agency and China's National Space Administration also had spacecraft operating in the Martian system. On November the 6th, Beijing released images taken by its Tianwen-1 orbiter. These images were not sharper than NASA's, but they were informative. They showed a diffuse coma surrounding a central nucleus. Consistent with the behavior of an active comet, there was no sign of rigid structure or artificial geometry. The object appeared to behave exactly as a comet should under solar heating. Despite the availability of international data, skepticism persisted. Some observers questioned NASA's explanations and accused the agency of minimizing anomalies. For those already inclined towards suspicion, the press conference did little to restore confidence. Avi Loeb once again became a central figure in the discussion. Within hours of NASA's briefing, he published a new blog post criticizing the agency. He argued that the press conference offered little beyond a restatement of known facts and failed to address a list of 12 anomalies he had previously outlined. According to Loeb, these unresolved issues deserved more direct engagement rather than broad reassurances. His response ensured that debate around 3I Atlas continued even after the release of official images. At the same time, the observational record itself remained unchanged. The press conference and the images released from the Martian system ultimately did not add any fundamentally new information. What they showed was consistent with what astronomers had already learned months earlier from observations made by the Hubble Space Telescope and the James Webb Space Telescope. The object displayed a diffuse coma, behaved in a way consistent with solar heating, and did not reveal any clear signs of rigid structure or controlled motion. Avi Loeb was quick to point this out. In his response, he argued that the briefing had largely repeated known conclusions rather than addressing what he considered unresolved questions. He closed his critique by invoking a line attributed to Sherlock Holmes: "There is nothing more deceptive than an obvious fact." The implication was clear. To Loeb, appearances alone were not sufficient grounds to dismiss deeper possibilities. As additional data arrived, Loeb's interpretations continued to evolve. Earlier, in October, he had framed the period around perihelion as a critical moment. Perihelion, the point at which an object comes closest to the Sun, is when it experiences maximum solar radiation. For a natural comet, this is when activity peaks. For Loeb, it also represented what he described as a hypothetical window of opportunity. He suggested that if 3I Atlas were an artificial object, perihelion would be the optimal time for it to activate. During that phase, the object was positioned behind the Sun relative to Earth, making direct observation difficult or impossible. Any activity occurring then would be partially shielded from view. One speculative scenario Loeb raised involved the release of smaller probes. He proposed that the object might deploy secondary devices toward planets it passed, potentially including Earth. He even framed this idea rhetorically by asking whether 3I Atlas might send probes as Christmas gifts for humanity. While the phrasing was clearly provocative, it reinforced how far his public speculation had moved from conventional scientific restraint. No evidence of such activity was ever detected. observations before, during, and after perihelion revealed no clear signs of probe deployment or anomalous emissions. Nevertheless, this absence did not end the theorizing. In early December, Loeb turned his attention to images captured after perihelion. These images showed a faint, teardrop-shaped glow extending in the direction of the sun. Such features are sometimes referred to as an anti-tail, an optical effect caused by dust particles distributed along the object's orbital plane and illuminated at certain angles. Loeb argued that this feature was not merely unusual, but potentially indicative of a swarm of smaller objects traveling alongside the comet. He stopped short of explicitly claiming these hypothetical objects were artificial. Instead, he posed a series of open-ended questions. If the anti-tail were associated with a population of non-evaporating objects, what were they? Were they rocky fragments? Or something else entirely? At other times, Loeb had suggested that the anti-tail could represent a beam of light emitted to clear debris from the object's path. This interpretation was even more speculative and was not supported by direct observational evidence. Still, it was presented as another possibility to consider rather than a definitive claim. By this stage, much of the broader scientific community had grown increasingly frustrated. Many researchers felt that the discussion had shifted away from evidence and toward repeated speculation that could not be tested with available data. Jason Wright, an astronomer involved in the scientific search for extraterrestrial intelligence, published a detailed series of blog posts responding directly to Loeb's claims. He examined each of the reported anomalies one by one and explained how known physical processes could account for them without invoking artificial construction. In one widely quoted passage, Wright wrote that zero planetary scientists gave Loeb's claims any credence. The statement reflected a level of irritation that had been building within the field. For many researchers, the issue was not curiosity about extraterrestrial life, but the standards of evidence required to support such claims. Their frustration was understandable. 3I Atlas was, by any measure, a remarkable object. It was likely billions of years old, originating from a long-dead star system. It represented a rare physical record of conditions that no longer exist. As a scientific target, it was genuinely extraordinary. Yet, the public conversation surrounding it had become dominated by speculation about aliens and accusations of government cover-ups. This focus overshadowed the careful work of scientists who had spent decades studying planetary formation, cometary physics, and galactic dynamics. In the process, the reputations of many researchers were indirectly affected. Scientists who expressed skepticism were sometimes portrayed as dismissive or secretive. Despite basing their conclusions on available data and established methods, Loeb's advocacy is best understood within this broader context. He has consistently argued that the scientific community is too conservative when confronting the possibility of intelligent life beyond Earth. In his view, skepticism has hardened into reflexive dismissal, limiting the scope of inquiry. Loeb has stated openly that he believes intelligent civilizations may not only exist elsewhere in the universe, but could already be observing or interacting with us in subtle ways. From this perspective, unusual interstellar objects deserve heightened scrutiny rather than rapid classification as natural phenomena. In his own words, he has argued that life is worth living if we allow for the unexpected to surprise us. He has contrasted this openness with what he describes as the preferences of bureaucrats or unimaginative scientists who focus only on expected outcomes. whether one agrees or disagrees. This framing helps explain his approach. To his credit, Loeb is correct about one important point. There are aspects of 3I Atlas that are not fully understood. Its composition, its metal ratios, and some features of its activity do not fit neatly into models developed from solar system comets. However, this uncertainty carries its own risks. Not knowing something does not automatically justify extraordinary conclusions. This is where many critics believe Loeb crosses a methodological line to understand why. It helps to return to the beginning of this story. Oumuamua was the first interstellar object ever detected. Borisov was the second. 3I Atlas is the third. That is the entire dataset. 3 examples are not enough to define what is typical or atypical on a galactic scale. In science, sample size matters. Patterns emerge only when enough examples exist to establish a baseline. With only 3 confirmed interstellar objects, there is no reliable definition of what normal interstellar debris looks like. This limitation lies at the heart of the debate. If we do not know what normal is for interstellar objects, then labeling something as abnormal becomes problematic. Differences in composition or behavior may reflect diversity rather than anomaly. Some critics have described Loeb's approach as a modern version of the God of the Gaps argument. In the past, unexplained phenomena were attributed to divine action. In this framing, unknowns are now attributed to aliens instead. When viewed this way, the debate takes on a different shape. It becomes less about whether extraterrestrial intelligence exists, and more about how science handles uncertainty. It is entirely possible that comets formed in other regions of the galaxy are fundamentally different from those we see here. They may contain different proportions of ices, metals, and dust. Their surfaces may evolve differently over billions of years in interstellar space. Without a clear understanding of what is typical beyond the solar system, it is difficult to declare any specific feature truly abnormal. That uncertainty remains the core challenge. Extraordinary claims require extraordinary evidence. That principle sits at the center of how science evaluates ideas that challenge existing understanding. At present, the evidence supporting the idea that 3I Atlas is an alien artifact remains thin. Nearly all of the arguments advanced in favor of that interpretation rely on circumstantial observations. These observations are not meaningless, and they are worth examining carefully. But they do not amount to direct proof. They fall far short of anything that could be described as decisive evidence. What is often missing from these discussions is how well 3I Atlas fits within existing models of cometary behavior when considered as a whole. When the object is examined in its entirety, rather than through a selective focus on individual anomalies, its behavior aligns closely with what scientists expect from a comet originating outside the solar system. This broader perspective is what NASA emphasized repeatedly. Including during the November press conference, the agency did not claim that an artificial origin was impossible. Instead, it stated that all available evidence pointed toward a natural explanation. That distinction matters. Evaluating evidence and arriving at the most likely conclusion is not the same as dismissing alternative ideas out of hand. It is a reflection of how scientific reasoning works in practice. By the time NASA communicated this position, however, public attention had already shifted. Conspiracy-driven interpretations had gained momentum. In that environment, any statement from the agency was interpreted by some as further confirmation of a cover-up. Even the release of images was reframed as suspicious. In such narratives, no outcome could falsify the claim. Evidence for natural behavior was treated as evidence of concealment. Beyond questions of interpretation, there is a more fundamental challenge facing the idea that 3I Atlas is an alien probe. This challenge is practical rather than philosophical. It concerns what current technology can and cannot detect. Humanity's ability to observe the solar system is far more limited than popular imagination often assumes. Even today, detection systems are incomplete. Less than a decade ago, the first confirmed interstellar object, Oumuamua, passed through the inner solar system before it was noticed. It was detected only after it had already traveled beyond the Sun and was on its way out. Since then, technology has improved. Survey programs have expanded. Sensors have become more sensitive. And data processing has accelerated. Yet even now, monitoring every object moving through the solar system remains well beyond current capabilities. Many objects go undetected, especially if they are small, dark, or fast-moving. Loeb's hypothesis relies in part on the idea that an advanced civilization might disguise a spacecraft as a comet to avoid detection. On the surface, this idea is not inherently illogical. Any intelligent species conducting reconnaissance might prefer to remain unnoticed. Masking activity behind natural phenomena could be an effective strategy. However, this reasoning raises an immediate question. If stealth were the goal, why construct an object on the scale of a small city? Early size estimates for 3I Atlas placed it on the order of tens of kilometers across, comparable to the length of Manhattan. An object of that scale is not subtle. It is far easier to detect than a smaller probe. From a detection standpoint, a vessel closer in size to conventional spacecraft would be far more likely to pass unnoticed. Large size works against concealment. It increases reflectivity, mass, and gravitational influence, all of which make detection more likely. Size also carries an energy cost. Regardless of technological sophistication, accelerating a massive object to interstellar speeds requires an enormous amount of energy. Moving something this large through space at velocities approaching tens of kilometers per second would demand resources far beyond what is necessary for exploration or observation. There is no clear functional advantage to building a probe of this scale. On the contrary, there are many disadvantages. It is harder to accelerate, harder to maneuver, harder to conceal, and harder to justify from an efficiency standpoint. At the time of writing, 3I Atlas remains within the solar system. It is expected to make its closest approach to Earth on December 19th. Even then, it will remain much farther away than it was during its pass by Mars, at a distance just under 2 astronomical units. This encounter will provide one final opportunity to observe the object before it continues outward and disappears back into interstellar space. After that, it will likely never be seen again. The window for direct observation is closing. The fact that months were spent debating whether this object might be an alien spacecraft reveals something important about the current state of human observation. It reflects not how advanced our understanding is, but how incomplete it remains. Modern sky surveys have existed for only a few decades. Even within our own solar system, we have not yet identified all significant objects. In the year 1989, only about 10,000 asteroids had been catalogued. That number represented a small fraction of what actually exists. In 2005, the United States Congress directed NASA to detect 90% of near-Earth objects larger than 140 meters across. That goal remains unmet more than 2 decades later. Detection stands at roughly 40%. Recent events illustrate these limitations clearly. In July of this year, an asteroid, estimated to be between 30 and 60 meters across, passed Earth at roughly 1/4 of the distance to the Moon. It was not detected until 2 days after it had already passed. And this is within a single planetary system. The Milky Way alone contains somewhere between 100 and 400 billion star systems. Most of them host planets. Many of them have ancient histories, extending back billions of years. Within that vast context, the possibility of intelligent life elsewhere cannot be dismissed. But possibility is not evidence. Until observations provide clear, unambiguous data, such ideas remain speculative. For now, 3I Atlas stands as a remarkable natural object. It is a rare visitor from another star system, carrying information about environments far beyond our own. What it ultimately represents is not proof of extraterrestrial technology, but a reminder of how much remains unknown, and how carefully those unknowns must be approached.